is also a very large source of neutrinos. And once again, you can calculate how many you should see, and you don't see enough. So let's start with the atmosphere. A cosmic ray comes in, hits a nucleus in the upper atmosphere, produces a pion, which, as we've seen, decays into a muon and a new mu. The muon continues, decays into an electron neutrino, and another muon neutrino. So obviously, for every interaction, you should have twice as many new mu's as new e. The ratio should be 2. This was investigated by several experiments, in particular 2 of them, one of them called Kamiokande in Japan and one IMB in the US, both of which used very large volumes of water, which were surrounded by light sensors, which we call photomultipliers. A neutrino went in and hits something in the water, giving you either a muon or an electron, and it was a matter of counting the muons and the electrons. Just to set the scale, here's a physicist in a scuba diving suit checking the photomultipliers. So it really is a big detector. And so what did they see? Well, first of all, you have to understand how you detect a charged particle in water. That's detected because it emits a Cherenkov light when it travels faster than light in that medium. Now, this doesn't violate any rule. The rule is that nothing can have a speed greater than the speed of light in vacuum. But in medium, light travels much more slowly, and charged particles can indeed travel at the speed of light in vacuum. So this can happen, and when this does happen, this Cherenkov light is emitted in a cone. So if this orange thing is the track of a particle, it starts emitting a cone at this point all the way along until it stops. So this succession of cones, when it hits the wall of light sensors, hits a ring of light sensors, and those then will have an electrical signal on them. And so if it's a muon, it'll be something sharp like this, and that's the kind of ring you will get. If it's an electron, on the other hand, remember I told you that an electron produces a little shower in matter. So each one of these electrons and positron emits its little Cherenkov cone in a slightly different direction. So the ring, instead of being sharp, will be a sum of rings, which gives you this sort of fuzzy nature to the ring. So it's a question of this gives you a muon, this gives you an electron. And the answer when they counted muons and electron was that the ratio was half what it was supposed to be. Now, unfortunately, the experiments were good, but they didn't have enough events. They weren't big enough to have enough statistics. So it was decided to build a much bigger detector and to see if the ratio really was 1. And at that point, they even also thought that the ratio was 1 because there weren't enough new mu's rather than more new e's. Fine, so discovery of oscillations. The big detector finally came into being. 41 meters high, 40 meters across, a cylinder filled with water, and on the inner surface of the cylinder were 11,146 hand-blown light sensors, each one of which 20 inches in diameter, beautiful glass dome, hand-blown. And you can see the detector before it was filled with water. And to set the scale, here are 3 men standing on a platform. So a neutrino comes in, and again, through the Cherenkov light, you can detect the electron and the muon, and you count them. 50,000 tons of water in Japan. Now, this detector was in a mine. You will see that very often, that neutrino detectors are underground. And the reason is that neutrinos interact very weakly, and so anything else can mimic a neutrino interaction, in particular cosmic rays coming from above, muons, protons, and whatever. So you want to protect yourself from cosmic rays by using the Earth as a shield. So here was a detector seeing neutrinos coming, produced above them, about 20 kilometers above them. So the neutrino traveled 20 kilometers between the point of production and the point at which they were observed. But since neutrinos traverse the Earth, they also observed neutrinos coming from below, and they were produced 12,000 kilometers away, so they traveled 12,000 kilometers, and any other distances in between. And what they observed was that the ones coming from above were just as was predicted without having to invoke oscillations or anything. On the other hand, the ones coming from below were heavily suppressed. And this was new news. New E's were just as expected throughout. And the conclusion was that the suppression came only over large distances. So if you wanted to fit oscillations with this, you needed, if you remember, a small mass difference for a large distance, and they measured m3 minus m2 to be 0.05 eV over c squared. Our unit of energy is the electron volt. That's the energy acquired by an electron as it drops through 1 volt. And the unit of mass, because E equal to mc squared, is eV over c squared. Sometimes we just use eV without the c squared. And this m3 minus m2 is referred to as the atmospheric mass difference. Now, physicists are a bit skeptics, so they start to say, well, oscillations is a big thing. Can we really say that